Good morning, students. Let's continue with the topic mapping process. Brief recap what we have discussed, and then we will continue with that. So, what we have discussed till now, that means why mapping process is needed, and what are the types of the mapping process. That is associative, direct, and set associative. Out of these three, we have discussed about the associative mapping, where no mapping functions are used and the respective data is copied from the RAM and placed in the cache memory. So this is all about associative memory, and we have also seen in the last lecture how we can define the size in the number of bits. That means how many bits are used to represent the address space. So this we have covered, and we have also covered uh, the cache memory is divided into number of blocks, that means, or cache lines we can also say this. So that means the few blocks can be transferred from RAM to cache memory on the basis of certain parameters, and parameters is defined by the mapping process. So we have gone through this, and we have also gone through this. If the cache is so the data, the respective data with respective to the address is copied from the RAM and placed in the cache. And we have seen with the example also, and this 15-bit address and 12-bit data. This 12 bits data should be same in the RAM and cache also. The bits should be fixed. So, and we have also seen this address bit and data bit is represented in the octal format to make it more simple to view. So it is represented. Now going into details about mapping process. So let's come with it. Let's start with the direct mapping. So till now we have discussed about the associative mapping where no mapping function is used. In the case of direct mapping and set associative mapping, there are different mapping function is used to store the data in the cache memory. So how we are doing? Using some mapping function, the data is transferred from the RAM and placed in the cache memory using some mapping function. So without going details to how the mapping function work, we will go the internal structure that will give some that give the idea how the data is stored in the cache memory after applying that mapping function. So first, in the case of associative, no mapping function is used. In the case of direct, some mapping function, modulo mapping function is generally used. So without going to what is the function, how that function works, that is. So indirect mapping I have written. Indirect mapping, the RAM is made of the stored data and made of the stored data, and it is stored in the respective cache also. So in this, generally, in the case of associative memory, the complete data along with the respective address is copied from the main memory and stored in the cache memory. So when the data is copied, there are many more copied in the unit of blocks, and it may contain some data that is not maybe not useful. So how to make use of that transfer so that we can get more informative data in the cache? And we already discussed, and we know that if we get the data in the cache, the access time will be very less as compared to the RAM, and if the access time is less, my performance will be high, the system performance of the system will be high. So how to store more number of informative data in the cache to increase my performance? So rather than blindly copying, where that is the case in the associative, rather than blindly copy the data or blocks of data from the main memory to the cache, we will apply some function. So how we will apply some function? In the case of direct mapping, that address field is divided into two parts. See, I have written the address space is split into two parts. What are the two parts? Tag and index. tag bits and index bits. So the cache used to store the tag bit, where the rest is used the memory. That means apart from many data, the only few data I am storing from the RAM to the cache, so that I can also accommodate more informative data in the cache rather than just useful data. So how we are doing? So we are dividing the address bits into two parts. What are two parts? Index and tag. And tag is stored in the memory as a informative data. See, I have written the cache is used to store the tag bit, where the rest is stored in the main memory. And so direct mapping is directly proportional to the hit ratio. So how many hits are there? So generally it will be divided into two scenarios. First, the transfer of the data from the main memory to the cache memory in the terms of blocks. And but now the block can contain one word also, more than one word also. So we will go through the both the cases. In this case, first we will discuss about one block size equal to one words. That means the data is transferred from the main memory to the cache memory in the terms of block, and one block will contain only one number of data word. So see, so so tags and index are used, so we can use this two parts, tag and index. So out of these two parts, what we have discussed, the tag is used stored in the memory, and the rest is stored in the main memory. Memory means cache memory. So tag part is stored. So to represent the cache, index part is used, and the respective few data with the tag is stored in the cache. Again I am repeating, to find the cache, or where to store in the cache, or how we can identify the cache, index part is used. And with respective to the index, data is stored along with the tag number. We will see with examples also. So see, I have written what I have told. Index bit is the number of address bits required to access the cache memory. That means how we are addressing, how many bits are used to address the total address space of the cache. That is defined by the index. If I ask you, let's the address is 15 bits, total address is. How many bits are in index and how many bits are there in tag? So how we will define? So index generally, the concept of the index depend upon the number of address bit required to access the cache memory. So let's discuss. So from the above example, we have also seen earlier also. So I have written again also. Size of the cache memory is 512. That means 512 bytes. So how many bits are required to represent cache memory? So 512, that means 2 to the power 9 is 512. So 9 bits are required to represent 512 address. That means the cache will store 512 data. Cache will store 512 number of data. So each data have address. So that means how many number of address are there? 512. So to represent 512 number of addresses, 9 bits are required to represent. So 2 to the power 9 by 2 to the power 9 equal to 512. So 9 bits are required. So index, how many bits? 9 bits. And we have seen the total address base. We have seen an example with the total address base is 15 bits. So 9 bits for index. How we have calculated 9? Because 9 bits are required for cache memory. So remaining 50 minus 9 equal to 6 bits are used for the tag. So tag is not given. We have to first find the index, and index bits are represented by this cache memory. So 9 bits are required, and the remaining 15 minus 9 equal to 6 bits are required for the tag. So how it will look like? See, the 15 bits divided into 9 bits for tag and 6 bit for 9 bit for index and 6 bit for tag. So this index, why I have written 3 bit only? Because it is in octal representation. So in octal representation, 3 binary bits is represented by 1 binary bit. So 9 bits are represented by 3 bits in octal. Similarly, 6 bits of tag is represented by 2 bits in octal. So see, 000 index with the tag becomes 01 and the data becomes 3450. What we have seen, I just going above to make it more clear. See what we have done. If the address base is 01000 and the respective data is 3450, so this address is divided into index and tag. So this three, the first 2 bits, this is the octal representation. So that means the first 2 bits represent the tag and the then the 3 bits represent the index. So that means the index is 000 and the tag is 01. And what is the data? 3450. And same for this. So see what I have written. Just I have just taken the same example. See, index is 000, tag is 01, and the data respective data is 3450. Again 00002 is the tag and the respective data is this. So this way it is stored, but there is a problem now arise. So that means this part is stored in the cache memory, the tag we have discussed. This part is stored in the cache memory, and this part is stored in the RAM, that is secondary main memory. So we can easily access this data using this tag and index. So this part is not required in the cache, just because this represents the address. This represents the address, and so this data is only stored in the cache memory. So when the address is divided into 2 parts, first, so this is extracted, the index part is extracted, and using that index we will get the tag, and using that tag matching we will get the data. But one problem arises. What is that? See, when we can access this index, so 000 with the tag 10 and 000 with the tag 02, these two tags 01 and 02 having the same index, and same index is not possible to store in the cache memory. So I have written this also. Two words with the same index cannot reside in cache memory at the same time, because this representing address of the cache memory. 9 bits are required to represent the address space of cache memory. So address space must be unique. If address space must be unique, so this index is used to represent the address. So these two are the same address. So when we are using only 2 bits, so this having the same address because of the index, same index. So these are not. That's why I have strike out this. That means either this will stored in the cache memory or this will store in the cache memory. So we have just lessen the space, lessen the amount of data to store in the cache memory, so that more data can be accommodated to increase the performance. So what is the demerit of this? Two words with the same index cannot reside in the cache memory. So this is all about the direct memory when one block equal to only one word. So now we will discuss if one block contain more than one number of words. Generally, one block contain 8 number of words in general cases. So we will go through this to see. This is what continue from the previous notes. So it is divided into assuming one block equal to more than one words, generally 8 number of words. So in the first scenario, what we have discussed, direct mapping, taking one block equal to one size, and in this we will discuss one block equal to more than one number of words, generally 8 number of words. In general scenario, there are 8 number of words. Index bit, it is a number of address bit required to access cache memory. So cache memory is 512. So now 9 bits are required. We have already seen. So let's say this one is important. If one block can store 8 number of words, this is also known as the block size. If I ask what is the block size, that means 8 is the answer. Why? One block can store 8 number of words. So the question arises, if the blocks can store 8 number of words or the block size is 8, how many blocks are there in the cache memory? So how we will find? So what is the size address space? 512, and 512 is divided into blocks and each block contain 8 number of words. So that means 512 address space store 512 number of words. That's why there are 512 number of address, because it will store 512 number of words. So 512 number of words is divided into blocks and each block contain 8 number of words. So if I divide 512 by 8, it will give number of blocks. So see, number of blocks will be 64. How we will say 64? 512 divided by 8, because each carrying 8 number of words. So there are 64 number of blocks. Now the question arises, now how we can represent the blocks? We have represent the index, we have represent the tag in the cache memory with the respective 40 bit data. But if there is a question arises of blocks, so how we can represent the block? So this, to represent this in the memory, this index bit is further divided into two parts. So in the first scenario, the index first scenario, the address base is divided into two parts, that is tag and index. And in this scenario, if one block contains more than one number of words, this index base is divided into two parts, what? Block and word. So 6 bits, again 6 bits. How we will get the 6 bits? You will find, if you do this, you will get the 3 8. One block contain 8 number of words. So 6 bits are required and 3 bits are required for the word, taking this scenario where the cache memory is 512 address space. So 6 3, total 9 number of bits are there for the index, so it is divided into 6 and 3. So how it will store in the memory, that I have also given. C, 15 bits divided into index and tag, and this is the respective data. I have taken the same data. You can just compare. When you study, just compare the data, how it is, how we are getting this data. See what I have done. This having the same index, I am, how we are defining the block. So this is block 0. Block 0 contains 001. So it will take 8 number of words. So 8 number of words means, see, index 000, 001, 002, 003, 004, it will go to 007. All are an octal form. That's why I have given the octal form. So 0 to 7, that means 8 number of indexes with the same index, with the same tag. That means the complete address is what? 01000, 01001, 01002. So it is divided into index tag. So rather than writing at the same time, same tag with the different index is stored in one block. Again, I am repeating, same tag with a different index is stored in one block, and it is represented in block 0, block 1. It will go till block 63. That means 64 number of blocks, 0 to 64. So this way you can, this way the data is stored along with the index and tag, and this is known as one block. So when it is stored in the cache memory, let's say this block, complete this block is taken from the main memory and stored in the cache memory. Again, let's say some data is required that is present in the block number 63. So that means this complete part is taken from the main memory and stored in the cache memory. So when you go through this, please compare all the data, because I have used the same data to represent the address as well as tag along with the data. So if you compare, it will be more clear how this works and how it is storing. So now see, we are here. So if same index having the different tag, see, same index having different tag. It's not possible right now, because see, same tag with the different number of index. So to represent this data, when one block contain more than one number of words, we have to do like this. We have to just what we are doing from that example, we are just dividing into block and words, and this defines the number of blocks. So with the same tag and same number of different number of index, same tag and different number of indexes, we are making in a group that is known as block with size 8. So this we are storing. So again, but what is the problem in this? If uh, this same index having the different tag, where I can store, so it will be very in the very end of the this chart. This again I am repeating, this index 000 with the different tag, let's say 00002, where I will found this. So it will be very at the very end. So at that time it again hampers my performance, because if the CPU needs same index with the different tag, same index with the different tag, so generally what it should be, 000 it will contain 01 tag, 000 contain the 0 tag. So it will be more easier to get the data with the different tag. But what in this block case, this contain the same tag with the different number of index. But if the CPU want to access the same index with the different number of tag now, so in the earlier case it is not possible. In this case, if it is possible, let's say it is possible, it will not get into block number 0, though the index is same, but I required different tag. Let's say I want 000 index, tag number 02. So I cannot get in block number 0. Somewhere I will get at the end, because after taking this iteration, again it will take 000 tag number 2, 001 tag number 2, somewhere at the end. That means when the CPU want to access the same index with different tag, it will take more time to access. Why? We will get more number of miss to get that hit, because I have to travel. I have to travel address wise. First, I will get the 000. First, then I will get 001. So all these are the address which is the same tag. After that, we will get somewhere around that 000 with tag 02, 001 with tag 02. So there I will get. So it will take more time. So again, this case, this hampers the performance. This slow down the performance, because the access time will be high. Because why high? Because the CPU cannot get the data with different tag for the same index. So it will again to overcome this, the concept of set associative came into existence. So we will discuss the concept of set associative in the next lecture. So please go through this. So see what I have written. The disadvantage of the direct mapping is that the hit ratio can drop if two or more words whose address having the same index but different tag can access repeatedly, because but such words are relatively far apart in the address range. So we have this thing we have discussed. That means index with the same index with the different tag 000 with tag number 02 will present somewhere at the end of this index space. So that means the hit ratio can be dropped, because such words are relatively apart from that. So this is the disadvantage of direct mapping. To overcome this, set associative mapping came into existence. So we will discuss the set associative in the next lecture. So please go through this. If you have any doubt, you can contact me. Thank you.